Previously, you got to see this graph where it involves some dotted vertical and horizontal lines. So these lines have names. They are called asymptotes. Here I have three pictures of three types of asymptotes. The first type of asymptote is called the vertical asymptote. There could be multiple vertical asymptotes in the graph. So this graph here, as you can see, there are two pink vertical lines, and they help shape the behavior of that rational function. The second picture is the picture of a horizontal asymptote. It's that horizontal pink line that you see there, and it also helps shape the behavior of this particular function. And the third picture is an example of a slant asymptote, where you see a slanted line. That's a pink line there. And that line also helps shape the behavior of the function. Furthermore, in that third picture, you also see a vertical asymptote at the same time. So they could coexist. So in this video, we are going to focus on vertical asymptotes, or I will abbreviate it with the letters VA. So the line x is equal to c, which is the equation of a vertical line, is a vertical asymptote of f of x if f of x approaches infinity or negative infinity as x approaches c from either side. To explain this statement, I'm going to draw a couple of pictures. First scenario could be where, let's say this is your vertical asymptote, and the behavior of the graph could either be going up on both sides of that vertical line. So as see, if f of x approaches infinity in this case, then x approaches c. So this is the vertical line is the line x is equal to c. It's approaching c from both sides. The next scenario, so we have this vertical asymptote. The function can also behave this way, where the function goes down to negative infinity as x approaches, again, the value c. The third scenario is where the curve would approach that vertical line from the left. And so in this case, the function is going up to positive infinity, and as x approaching c from the left. And then on the other side, the function will go to negative infinity as x is approaching c from the right. And in the last scenario, just the opposite. This is where the function could go to infinity as x approaches c from the right, and the function could go to negative infinity as x approaches c from the left. To find the vertical asymptotes of a rational function p of x over q of x, we are going to do the two steps. Step 1, simplify the rational function to make sure that p of x and q of x have no common factors other than 1. Step 2, let the denominator equal 0, then solve for x to get a real zero c. Then x equals c is going to be the vertical asymptote. A few things to note here. There could be multiple vertical asymptotes in the graph. As you can see from the first picture here, there are two vertical asymptotes. Second, the graph may not cross a vertical asymptote. So let's do these examples following the two steps. So the first step is we want to simplify this by factoring. So the numerator cannot be factored, so we're going to keep it this way. And then the denominator, we can factor this using the AC method. So A is 3, B is 5, and C is -2. Two numbers multiply to A times C, so that's -6, and add up to B, which is 5. So the two numbers can be +6 and -1. 6 times -1 is -6, and 6 plus -1 is +5. So rewrite the middle term as 6x minus 1x and keep the first term and the last term. Factor by grouping. Factor out 3x. We have x plus 2. Factor out -1. We have x plus 2 again. Factor again with x plus 2 being the GCF. We have x plus 2 times 3x minus 1. Now we are going to put the factor form in here. The numerator cannot be factored, so keep that the same. Denominator x is x plus 2 times 3x minus 1. I don't see any common factor to cancel, so we completed step 1. Step 2 is to let the denominator equal 0, so we're going to let x plus 2 times 3x minus 1 equal 0. So that means x plus 2 is equal to 0, or 3x minus 1 is equal to 0. Solve each of these linear equations. We get x equal -2, or x is equal to 1/3. So these two right here are the equation of the vertical lines that are the vertical asymptotes. So these are the vertical asymptotes. And they are not just values, they are actually equation of a vertical lines. Second example, where we have 4x squared over x squared plus 4. A very common mistake, students might try to cross out x squared with x squared. However, they do not cancel, as the numerator, x squared here is a factor, but in the denominator, this x squared is not a factor. So because they are not both factors, you cannot cancel them. And I see that the denominator, x squared plus 4, cannot be factored either. So our next step would be step 2, where we are going to just let the denominator equal 0. So subtract 4 from both sides, you get x squared is equal to -4. However, we have a problem. The next step, naturally you would take the square root of both sides, but we can't take the square root of a negative number since we're dealing with real numbers. So therefore, this equation actually has no solution. And because it has no solution, we can say that this one has no vertical asymptotes. Next example, we have the numerator is 2x squared plus 5x plus 3. Let's see if we can factor that one using the AC method. So product equals A times C, which is 2 times 3, and that's 6. Sum is equal to B, which is 5. So the two numbers should be 2 and 3. So we're going to rewrite 2x squared plus 2x plus 3x. So rewrite 5x as 2x plus 3x, and then bring down that last term. Factor by grouping. So we have 2x here as the GCF, x plus 1. +3 here is the GCF, x plus 1. Factor again, we have x plus 1 times 2x plus 3. So put it back in here, we have x plus 1 times 2x plus 3 over x plus 1. So you do see a common factor, which is x plus 1. But after you cancel the x plus 1, we no longer has a denominator to do step 2. So because of that, we also say that this one has no vertical asymptotes.